In 1985, Mexico City's deadliest earthquake killed over 10,000 people. But here's what nobody talks about. Buildings constructed in the 1950s survived. Buildings from the 1970s collapsed. The newer buildings were more dangerous. And the reason why reveals everything wrong with how we think about earthquake engineering. What you're about to discover isn't just about steel and concrete. It's about invisible waves that turn solid ground into liquid. It's about buildings that dance with destruction instead of fighting it. It's about a single frequency that can turn a skyscraper into a tuning fork of death. And it's about why the tallest buildings on Earth might actually be the safest place to stand when the ground starts shaking. Most people imagine earthquakes wrong. They picture the ground cracking open, swallowing buildings whole. But that's not what kills. What kills is invisible. When tectonic plates slip, they release energy in waves. These waves travel through rock, soil, and sediment. And as they travel, they oscillate at specific frequencies. Think of it like sound. Low bass notes, high treble notes, everything in between. The ground during an earthquake isn't just shaking. It's vibrating at particular frequencies, sometimes for minutes at a time. Now here's where it gets dangerous. Every building on Earth has a natural frequency, a rate at which it wants to sway. And if the earthquake's frequency matches the building's frequency, resonance, the same phenomenon that lets an opera singer shatter glass. In 1985, Mexico City sat on an ancient lake bed, soft clay sediment. When earthquake waves hit that clay, something catastrophic happened. The sediment amplified waves at around 2 seconds per cycle. And you know what else has a natural frequency around 2 seconds? Buildings between 8 and 15 stories tall. Those 1970s mid-rises weren't poorly built. They were accidentally tuned to die. Shorter buildings oscillated faster than the earthquake waves. Taller buildings oscillated slower. But those mid-rises? They caught the wave perfectly. Each oscillation added energy. Back and forth, growing stronger, until concrete cracked and steel buckled. A building's height essentially determines its heartbeat. Change the height by 3 floors, you change whether it lives or dies. So how do modern skyscrapers survive? The answer seems counterintuitive. They're designed to move. Early earthquake engineering made a critical error. Engineers built structures to be rigid, assuming stiffness meant strength. They were wrong. Rigid buildings don't absorb energy, they accumulate it. Every wave adds force until something breaks. Modern seismic design embraces flexibility. The goal isn't to resist the earthquake. It's to redirect its energy. This starts at the foundation. In traditional construction, buildings connect directly to the ground. Every vibration transfers straight up into the structure. But in base-isolated buildings, the structure sits on flexible bearings, usually layers of rubber and steel plates. When the ground moves, the foundation moves. But the building above stays relatively still, gliding on its isolators like a hockey puck on ice. Japan's Narita Airport uses base isolation. During the 2011 Tohoku earthquake, magnitude 9.0, the terminal barely swayed, while surrounding areas were devastated. Some base isolators in Tokyo can move nearly 3 feet in any direction. The building literally slides around during an earthquake, while people inside keep working. But base isolation alone isn't enough for super tall buildings. You can't put a 1,500-foot tower on rubber pads. The physics don't scale. So engineers developed something else. Imagine you're standing on a moving train. To stay upright, you instinctively lean against the motion. Your body becomes a counterbalance. Skyscrapers do the same thing, but with massive engineered weights. They're called tune mass dampers, and they're one of the most elegant solutions in structural engineering. At the top of Taiwan's Taipei 101, there's a 730-ton steel sphere, suspended by cables, surrounded by hydraulic pistons. When typhoon winds or earthquake forces push the building in one direction, the sphere swings the opposite way. It's a pendulum working against the sway, absorbing kinetic energy and converting it to heat through the hydraulic dampers. During a magnitude 6.8 earthquake in 2002, cameras captured the damper swinging over 3 feet. The building occupants barely felt it. That single steel ball cost $4 million. It saved potentially billions in structural damage. But here's what most videos won't tell you. Tune mass dampers only work for the frequency they're tuned to. The ball in Taipei 101 is calibrated for one specific sway period. If earthquake waves hit at a different frequency, the damper's effectiveness drops dramatically. Which brings us to the most radical earthquake technology ever built. Something that doesn't just dampen earthquakes, it predicts them. And it's protecting buildings right now in ways that seem impossible. In 1964, Niigata, Japan experienced something that rewrote engineering textbooks. During a magnitude 7.5 earthquake, apartment buildings didn't collapse. They sank. They tilted. They rotated in place like toys pushed by a child's hand. The ground beneath them had transformed. This phenomenon is called liquefaction, and it's terrifying. Certain soils, sandy, loose, water-saturated, behave strangely under vibration. The shaking causes water pressure to build between soil particles. The particles separate, and suddenly, what was solid ground acts like thick liquid. Buildings don't crack. They just lose their footing. Modern skyscrapers deal with liquefaction by going deep. Really deep. The tallest buildings don't rest on soil at all. Their foundations extend down hundreds of feet until they hit bedrock, solid, ancient stone that can't liquefy. The Burj Khalifa's foundation includes 192 piles driven 164 feet into the ground. Shanghai Tower sits on a concrete mat 20 feet thick, supported by nearly 1,000 piles. Engineers designing the Salesforce Tower in San Francisco drove piles through 60 feet of mud to reach bedrock. The foundation alone took 2 years. Now, that radical technology one mentioned. In Japan, some buildings now have sensors embedded at their foundations and throughout their structure. These sensors detect the primary waves of an earthquake, the faster, less destructive P waves that arrive before the damaging S waves. Within milliseconds of detection, the building's systems respond. Elevators stop at the nearest floor. Gas lines shut off. In some advanced systems, active dampers engage, powered pistons that push against the anticipated motion before the main shaking even arrives. The building is preparing for an earthquake that hasn't fully hit yet. This is earthquake early warning integrated with active structural control. It's not science fiction. It's operating right now in Tokyo. What strikes me most about earthquake engineering isn't the technology. It's the philosophy. For decades, we built structures to resist nature, to stand firm, to be unmovable, and they failed. The breakthrough came from accepting that we can't overpower an earthquake. We can't stop tectonic plates. We can only learn to move with them. Flexibility, adaptation, controlled surrender. Every skyscraper standing in an earthquake zone represents this shift in thinking. From dominance to cooperation, from rigidity to resilience. And that raises a question I genuinely want to hear your thoughts on in the comments. If our buildings have learned to survive by moving with forces instead of against them, what else in engineering, or in life, are we still trying to fight when we should be learning to flow? If this made you see buildings differently, subscribing helps this channel keep breaking down the hidden engineering shaping our world. The ground beneath you is always moving. You just can't feel it yet.